This video is sponsored by PCBWay.
Hey there, this is Seth Schaefer from Team Just Cause Robotics, and in today's video I'm going to talk about the design process that I go through to design a competitive 3-pound beetleweight combat robot. This one right here being called Derivative, that's about to compete at the November 1st NHRL, and the many other complications that made it so that even though I had this design 3 months ago, I decided to abandon it and completely redo everything from scratch at the start of this month, even though the competition is on November 1st. So this bot's going to be competing in 11 days, and I've still got some last minute tweaks and changes to make, which I will talk about. So in this video, I'm just going to talk about how me, as somebody who's been competing competitively in the combat robotics world since 2017 and worked professionally as a mechanical engineer for several years before quitting to run a combat robot company full-time, approaches the design of a brand new combat bot. And you'll be able to learn with me along the way what things I'm thinking about when I go about doing the 3D modeling and design choices for any of my bots. All right, I'm gonna leave out some of the details that I did the first few attempts I made recording this because otherwise this video is gonna be an hour long. Let's first talk about this thing. This was originally going to be Derivative, although at the time I had no idea what I was gonna name it because I hadn't even entered the NHRL event lottery yet. But I commissioned this design from a builder on the NHRL Discord who goes by the username Rinsler, or just name DJ when he's competing. And Rinsler designed this entire chassis for me about 3 months ago. I paid him for his time. I am not telling him that he's, doesn't deserve the money that he was owed. He was paid, I think whenever he asked me for money, he was paid right away. But I forget if that was up front or just within a couple of weeks of when he started. But either way, his time was compensated. He actually did make some design tweaks to this for me after I paid him too, because I had some issues with transferring everything from Onshape, where he designed it, into Fusion 360, where I work, and he, relabeled some things to make it a little bit easier for me to work with his files. But ultimately, there were too many issues with this design, and the experience that I have making many, many robots that are meant to be mass manufactured from my experience selling the SSP kit, and the fact that I was at least considering trying to make this robot potentially a kit that people will be able to buy in the future, I'll talk about that more later, meant that this design wasn't really going to work for me. There's kind of 3 main reasons why I had problems with this design, and I think most of them aren't really DJ's fault at all. There's like one issue that's kind of his fault, but is something that's really easy to overlook and something that I could personally have very easily fixed, so not like a huge issue or anything. And that is just the fact that right now the drum spinner hits the floor. These teeth go like just below, I don't know if you'll be able to see this, but the teeth go like just below the aluminum uprights here, and so it hits the floor all the time. Now, it's designed to have forks bolted on. In fact, I can click over to my overlay view. So this is what the bot's supposed to look like. So these forks do stick down far enough that the drum definitely can't hit them, and that's not a problem normally, but this is a combat robot. Those forks are for sure going to get torn off, and so that was not really good enough for me personally. And also because of the flexibility of TPU and everything, like even with those forks bolted on, I had issues with the fork just like tilting up and the drum could still kind of graze the floor a little bit, so I just wasn't super happy about that. So the second biggest issue is the assembly process to get the drum on and off of the bot. So the way that he designed this is actually pretty clever. So there's kind of 3 parts here. This big TPU wheel guard, this big TPU wheel guard, and then this main body. So those pieces kind of fit into slots here, and then there are TPU pins that go in to hold them in the back. In the front, however, they screw on with 4 screws here, and that's not a huge issue, but these 2 aluminum pieces are taking like all of the force. Every time this robot hits anybody, drum is spinning like this, so it's going to hit another robot, and it's going to try and plant this into the floor, so all the force path is going from this shaft in the middle straight down to the floor through these aluminum pieces. But those aluminum pieces aren't the only thing that the shaft is passing through, because it's actually passing through a little bit of the thickness of the TPU on this side and a little bit of the thickness of the TPU on this side as well. So to actually assemble this, you have to fit that shaft through TPU, then aluminum, then a spacer, then this part of the drum, then 2 spacers, then the stator of the drum, then this piece of aluminum, and then this piece of TPU, which is extremely, extremely annoying. So I just found from taking this apart and putting it back together like 3 or 4 times, serviceability in the pits was not really where I wanted it for this design. And then that could have been fixed. That we had, Rinsler and I talked about ways to fix that, which would be pretty simple. Make these pieces, instead of a 1/4 inch wide, be 12 millimeters wide, which is how I designed the shaft length for the drum, was to go through either 1/2 inch thick or 12.7 millimeter, or just 12.0 millimeter thick uprights. So if these were all aluminum that was just 12 millimeters thick, that would kind of completely eliminate that problem. And that wouldn't be a real issue. So again, this is the sort of design change I personally could have made if I felt like it to fix things. But yeah, I just didn't decide to go that route because of the third major issue, and that is 3D printing these would really, really suck if I had to make like 10 or 20 or 30 or 50 of them, because each bot requires printing 2 of these pieces in this orientation on the bed like this. So there's a ton of 3D printed supports under here. So a pair of these takes 5 hours. And then this central body also takes 5 hours. So that's 10 hours of print time per kit on a high-end Bamboo Lab X1 Carbon or P1S 3D printer. And I can't even print both the chassis and the side guards at the same time on my A1 Mini, but I can on the X1 or P1. But still, that's 10 hours of printing per chassis, a lot of chances for something to go wrong and lose a lot of filament in that process. And I'd just be churning through so much filament. Right now I sell the SSP combat robot kits. Those use a billet UHMW machine chassis. It's really, really expensive, but it's, in my opinion, kind of just the best. For this, I want to do something a bit cheaper because this weapon system is really expensive, even in bulk. So to make the chassis cheaper, I actually bought a CNC router about a year ago, and I plan to fabricate all the chassis in-house right here in America myself. Now, machining plastics on a home CNC router is pretty easy, but machining metal can be very hard. Unless you're spending more than probably whatever car you own would cost brand new, you're probably not getting a machine that's built from the ground up for machining aluminum, let alone steel or something harder. That's why when I need aluminum complicated parts made, I'm turning to my longtime sponsor, PCBWay, to get them. PCBWay has been working with me for a very long time, since I think around 2023 actually, and I've gotten a ton of awesome machined aluminum parts from them that, while technically possible for me to machine at home, would be an absolute nightmare and use up way too many hours of my time. And when often buying 7075 aluminum stock costs more than what the part finished and machined and shipped to my door would cost from PCBWay, I'm always going to be turning to them in the future. Right now, they're actually making a new version of the SCARAB hub drum, and I will show you what that looks like right here. This is the part they're making for me, and hopefully it gets delivered in time for the November 1st NHRL, and I'll talk about why I ordered this later in this video. At just about $100 a piece, it was maybe a little bit cheaper to buy stock and try and machine it myself, but considering it would have taken me easily probably an entire 10-hour workday just to make one of these drums the first time, I thought it was well worth it to just spend $100 and have PCBWay do it for me. If you make more than like $20 an hour, it'd be worth it for you too. So make sure to check out PCBWay at the link down below and get $5 off of your first order. The reason that I can do that with these and not with the SSP kits is that these parts are all be able to be machined from the top down on a single sheet of material. And I'll show you exactly what I'm talking about. So this is what the frame of the robot looks like, and it's 4 parts, right? You've got left side rail, the mirrored left side rail. You've got, this is the same exact thing, just flipped upside down. And then we've got the front panel, and we've got the rear panel, which is that one. So 4 pieces. You'll notice the thickness of this is 12.7 millimeters, or 1/2 inch, because you can buy 1/2 inch stock here in America much more easily, but every other dimension on here is actually kind of designed in metric for the most part. So like this is 102 millimeters wide. That's the spacing needed for this drum, for instance. And the overall length is 156 millimeters. And then the height is 35 millimeters, not including the lids. So from here to here, 35 millimeters exactly. So I did everything in metric because I am an engineer in America, therefore I am cursed to always be switching between imperial and metric measurements. Sue me. So this frame uses all 1/2 inch thick parts for the sides, the rear, and for the front, it's 8 millimeters thick. I can change this to whatever I want, but I decided it doesn't really need to be that thick in the front because this isn't really supporting anything. It's just kind of there to be a barrier and not prevent the battery from, and to prevent the battery from like sliding into an active spinning drum. And it also needs to have screws to support the lid, so it needs to be thick enough for that. So this is what that looks like on my CNC table, basically. All these parts are cut out of a single 1/2 inch thick sheet, and I just face it down to 8 millimeters thick on this part, and then everything else is just machining the same stock thickness. So I don't even have to face off anything else really. And I can just go top down, single operation, cut out everything, leave tabs, cut those tabs with the oscillating multi-tool later to separate the parts, maybe sand them a little bit, and that's pretty much it. So everything else can be done by my CNC except for these holes on the edges. So to do that, I came up with a separate jig that I'll show some video of in action, but that jig is actually just 3D printed in PLA, and it just allows me to slot these into slots like a toaster, and then machine the holes all the way through. I can just drill them all. So that drilling process takes like 10 minutes or something. It's kind of slow, but not too bad. And the processing time to cut out an entire frame like this on my CNC is maybe half an hour, plus 10 minutes of drilling. So we're talking like 40-45 minutes of total machine time per chassis instead of 10 hours of 3D printer time. And I can batch these out, so I could just have the machine cut up to 4 of them at a time out of a single 12 by 24 inch sheet of material, which is really, really convenient, because then it's just like 2 hours of machining at a time basically, or maybe like a 4-hour day, I could get 8 frames done or something like that. So really not too bad for mass production. Yeah, so I decided to abandon this idea and move on with this idea. And the internals of this are very, very similar. So I guess I may as well just go back to the CAD view and you can see it. I mean, you were just looking at it, but I'm using the same exact Blitz Pro drive motors, same exact battery for right now, though I did order some custom batteries, same exact wheels, although I also ordered some custom wheels, which the supplier, of course, naturally told me would take 20 work days to produce, which is, you know, about 4 weeks, and it has now been 9 weeks and I don't have them yet, so may or may not be running the urethane wheels that are on there right now at NHRL, but we'll see. And yeah, the same exact SCARAB drum weapon, of course. So if we go back to my webcam overlay view here, so you can see the SCARAB beta drum on here, exactly the same as what was on the TPU copy of the robot. And, you know, instead of having aluminum and TPU, I just have 1/2 inch thick UHMW, and the shaft bolt passes all the way through those. Super easy to service because there's nothing blocking your access to this either. So like with the side guards on here, like you can't access that bolt anymore until you unbolt the side panel. So you have to pull out this pin, undo 4 screws, pull this off, undo this bolt, undo these 2 bolts, undo these 2 bolts. Same on this side. Like it's like so many more operations to service the drum on this. Whereas on this version, all you have to do, this looks a little bit messed up because there's something weird with the side panel, but basically you remove like these 2 screws on the opposite side for the stator, and then remove this nut and bolt, pull the bolt through, and you're pretty much good to go to swap the drum completely. And if you want to pull the entire side off the robot, that only requires removing these 3 screws, and then the same on the other side, on the top. And then you can pull an entire side of the frame off as well to get the drum back in much more easily. So everything is kind of tabbed and slotted together. If you watched my integration video, you'll know that my frustrations with tab and slot construction being done improperly were quite great in that video. So I did it myself this time, knowing that it would be done correctly. So when you're designing something to be CNC machined, it's being cut with a round end mill, so you can't make sharp internal corners. You can make sharp external corners, because you can have, you know, imagine this, right? Here's my end mill. It's 0.125 inches in this case. So the end mill can travel in 2D space. It can do this path. But if it gets to here, you know, and then it goes up, then you've got a radius in this corner right here. So you can't actually slot, you know, this square into, you can't slot the square peg into a rounded corner hole. So that's why the end mill has to go past there. It has to go into this pocket here. And that way I can have like effectively a sharp corner, just not really. And so this all tabs and slots together. So the rear the side panel looks like this. The rear panel looks like this. That slots in. And then the front panel, what I did, instead of doing a tab and slot thing where I had a rib that sticks into the side panels, because then I would have had to have dog bone corners in 4 places or something. Instead, what I can do is take advantage of the fact that the sides, all I really have to do is cut a channel like this. So I can have the end mill pass all the way out of that side, all the way out of this side, and make essentially a nice square cornered sharp pocket on this piece. And then on the front, these can also be square corners because they're just going into this slot full height. So on one side, there's a gap because the wires for the actual hub motor drum fit through here. So they go in around here, go down this way, through that front panel gap, and then they come out into the chassis over here. So I can show you on the actual robot. Hopefully it'll let me click on it. So that's that wire path on the actual robot. So you can see it passes through that gap in that front panel. So there's tons of clearance. It's pretty easy to get the wires through here. That was also a huge struggle on the TPU version, but again, that's something that could have been fixed. So yeah, as far as getting the hub motor on here, it should be way easier to put it on and take it off. Then we've got the drive system. So the drive system is my Blitz Pro drive motor, same that Division version 4.5 is using, but I'm using gigantic wheels. These are 70 millimeters or 2.75 inches in diameter. And so the motors, if we take a look at the side rails again, I just pocket into here. Again, I'm dogboning these corners a little bit and kind of having the end mill go past because there's otherwise kind of a sharp corner here. So front face of the motor is grabbed here. It can't rotate because there's a square imprint on it that gets locked by these faces. And then the round gearbox gets supported partially by this feature. And this is just a through holes for the shaft and circlip and everything to get through. So just a big, much bigger hole than I needed. I think I did an 8mm hole for a 6mm shaft. So this gives you a better idea of how exactly the gearbox integrates into the frame. So if we look at there, it's about halfway through everything. Kind of seeing the internals of the gearbox, that's a little confusing, but you can see exactly here. So that's like the round portion of the gearbox, and then the square face plate you can see up here. And if I hide the side panel temporarily, you can see exactly what the front of the gearbox looks like. So you've got that square imprint. Go back to my cutaway view and put back on the side rail. You can see how it pockets nicely in there. And then I've just got clearance for M3 screws here. And that's pretty much it. So pretty simple. And then these wire guards, I took inspiration from how DJ did it in his design. I actually quite like that because there's no hardware needed to install these. They just kind of get slotted onto the motors from the bottom, and then you put the base plate on and that retains them. And they just can't move forward and back because there's no clearance, which I really liked. So I stole that feature. I redesigned these from scratch, but I stole that feature of his design for my own. And there's just slots on both sides for this wire channel to come through so that these two parts are 100% identical. Side panels, again, on the production version of this, the side panels will also be 100% identical. It's just on my version right now, because the hub motor wires exit straight through this way, I needed 2 different ones. That's why this looks kind of funky with these like overlapping holes. There's like 2 side panels on top of each other in the 3D model, but once I have production versions of these hub motors, the wires are going to exit at a right angle, just straight back, just go through this gap. And then both of the side panels will actually just look like this one here, where I don't need a channel that continuously goes through to let the wires through anymore. So yeah, it'll be a little bit stronger, not a huge difference, but mostly just you'll be able to use this third screw in the middle without worrying about it going into your hub motor wires. So yeah, I think that explains most of like the main important surface level things about this design. So let's take a look quickly at the back panel. So the back panel has one of my classic PCB switches just like pocketed into it. And that way it takes up basically 0 space internally, except for the wires. You'll notice there's like a kind of funky looking pocket here. The reason for that is the switch is, sitting in here. The backside of the switch is going to be parallel with these surfaces, but then you're going to have wires coming in and they want to exit somewhere. So I figured I can just leave these channels here so the wires have space to exit out the side and like bend out here. Because if I just made this all just like a rectangular pocket with a switch in it, then the wires would have to stick like straight out, and that would be a much weaker connection that's more likely to break and harder to solder that way. So doing it this way was just simpler. The back panel is completely reversible as well, so if for some reason you're like, maybe you're left-handed and you really want your power switch on the left side instead of the right, you can actually just straight up flip it so that this is flipped 180 degrees and the switch is on the left side instead of on the right side. But I just modeled it with it on the right, and I think when I built it, I actually did it by accident so that the switch is... actually, no, I did it correctly with the switch on the right on this copy of the bot. Oh, no, right. No, this is upside down. Okay, yeah, so I accidentally put the switch on the left side on here, and no big deal because all I have to do is design a new piece of this TPU that has the holes on both sides, but this one I just flipped upside down. It's a little bit asymmetrical because, you know, obviously you don't want your bot to be able to get stuck on its back. I don't have that modeled in CAD, but you don't want the bot to be able to balance on its back. And by making this a little asymmetrical, my idea was that it more often will end up rolling onto right side up rather than upside down. If I just made a single curve, not only would it be 50-50, but it would also roll over slower because the center of mass could potentially be balanced perfectly on that center of curvature. Whereas here, the center of curvature is off to the side here, so it'll always want to tip this way if it ends up in that situation. And the side panels, same way, they are rounded. These ones, for aesthetic purposes and also practicality purposes, I made these symmetric because I want this to be able to be flipped upside down and put on the other side as well. So they kind of have to be symmetrical, so I just live with it being 50-50 whether it falls onto this side or that side. But self-righting with this is actually really fast and easy because it kind of does the like Minotaur style gyroing thing. And there's a ton of ground clearance, you'll probably notice with this. Tons of ground clearance, which I wanted just so I didn't have to worry about getting stuck on anything. Ground game isn't nearly as important with this style of robot as it would be for something like Division, because the drum is like really out front there and it'll hit whatever it runs into. But I did leave extra holes that you can just add forks by bolting them on if you choose. I don't think that if I do make a kit version of this, I don't think it'll ship with any forks. I might sell some as a separate add-on, but I think it would be a little bit too try-hard of a turnkey kit if I included ground game out of the box as well. But pretty much everything else you should be able to buy. I might even do a version where you can get it a little cheaper with none of the 3D printed TPU parts, just the machined frame and other parts like that, and then print your own parts to save a little bit of cost if you were going to make it a custom color anyway, which a lot of my SSP kit owners end up doing. So yeah, I think that covers all the really important key aspects of this bot. Now let's talk about the SCARAB Hubmotor drum and what exactly needs to change with that. So I'm going to show some test footage of me destroying a very expensive custom Hubmotor, and I guess look away if you have sensitive eyes. So I have sent 50 of these beta drums to a bunch of people, and not that many of them actually tested them in combat, which was kind of disappointing and part of the reason that this has taken me so long to get the production batch out. But I wanted as much combat testing feedback on this product as possible because it is one of the most complicated and difficult product design experiences I've ever had. Obviously, like the entirety of the SSP kit was much worse, but as far as like an individual like part that goes on a robot, this has a lot going on. First of all, it's got a stator, magnet ring, and that together makes up most of a motor, but then you have to have the shaft, you have to have bearings to support the rest of it, you have to have the aluminum hub, which is really complicated, and I had to try and get as many features as possible into it without this cost skyrocketing, and it needed to be super durable. The beta ones are made out of 7075 aircraft grade aluminum, and the teeth are made out of AR600, which I had to make a custom rig for my CNC to bevel, and I ruined like probably $100 in end mills doing that. It was really terrible. I'm definitely not doing that again. So there were kind of like three key issues that I wanted to solve with the next version of the drum. Number one biggest problem with these beta ones that a lot of people have dealt with, not everybody, but a lot of people, is that the teeth can get ripped off. And the way in which they get ripped off is generally just that these M5 bolts, which are only about 5 millimeters deep into the aluminum, as especially you can see in this cutout here, these M5 bolts just like get yeeted out. They just tear the thread straight out of the aluminum. Now, I didn't think this was going to be a problem because my 4935 or Cherry Bomb motors, I have a same thickness blade bolted on with same size bolts with the same thread engagement, and those keep the blades on. But the big difference, it turns out, is that this tooth is really wide. And so what happens is, especially with this tooth here, if this hits on like a corner of another robot, basically all the force ends up going through just this one screw. And so it can actually bend, and on top of that, the tooth is relatively like thin in the back. It's not super thin, but for like an AR-600 weapon, like kind of thin. So I actually had a case where the entire tooth like bent up and just this screw got popped out. And you can only imagine how it kind of just like zippers out from there once you've got some of the support removed and another hit comes. And that's just with this hitting a 3-pound block of aluminum, not even another vertical spinner or another drum spinner. So I can only imagine how easy it would be for the screws to get ripped out in an actual fight. And I saw it happen in person at Mass Destruction in the 2-pound multi-bot that ended up winning the event, Sibling Rivalries. They had a tooth ripped out in their very first fight, and then their second Hubmotor drum that they had as a spare was able to get through like 5 more fights and win them the entire tournament. But obviously, having one drum destroyed in like 6 fights is still pretty terrible, in my opinion. That's not the level of quality and durability that I expect out of my own products, and certainly I don't think you should expect that level of durability out of a product. There are aspects of this that I really did like, though. For one, the motor has tons of power, and for two, the replaceable magnet rings is definitely an idea that I'm keeping, because it's going to make it so that you can use these drums for a lot longer without having to buy a whole new aluminum hub, as long as I can solve the threads being ripped out, of course. So yeah, the second issue, like I talked about before, is just that cable management problem. And the third problem that I had was just, in general, the teeth were wearing a lot faster than I expected for AR-600. I think it's just because it comes to such a sharp edge. So I'm going to be changing the teeth to S7 tool steel hardened to 53 to 55 HRC, and they are not going to be as sharp. So what you're looking at here is a SCARAB version 1.1. The beta ones I didn't really have a version number attached to, but tentatively let's call them version 0 point something. Version 1.0 was my first attempt at what the production one was going to look like, and it kind of just looked like this, but with 6 screws and more thread engagement everywhere. But I decided to go a completely different direction after I tested this out with steel threaded inserts and still had the threads being torn out because of how much force gets concentrated on individual screws. So I took some inspiration here from a robot called Warhard, which currently uses a machined single-piece titanium beater and a belt drive system, but in a previous rendition, it was still belt drive, but they had an aluminum drum with steel teeth in a similar style to this. And what I really like about this style is that the steel teeth impact on this surface, not on just a tip here. And then it's just pressing straight back into this aluminum with like very little overhang here. There's very little like leverage trying to pop screws out. The worst thing that'll probably happen with this is if you're spinning slow enough or you're going against another drum that's spinning similar speed, these tooth heads are sure gonna get mangled, whatever. But screws are really easy to replace. And if a screw head gets beaten up but not torn off, then this tooth stays attached. And more importantly, I can just have like a lot more material right behind the tooth. So instead of 5mm in thread engagement with M5 by 10s onto a 5.3mm thick tooth, these are now 5mm thick exactly. And then these are M5 by 16s. So they have like a solid like 9, 10, 11mm of thread engagement. And that way, even if the forces on them was the same as before, it would be like 3 times stronger with 6 of those screws with way more engagement each. So there should be no issues, hopefully, with this like zippering apart. And I still kept the kind of like asymmetric design. It's not nearly as pronounced, obviously. There's much less of a difference between the height here and height here. But you'd be surprised with how fast these things spin. 36,000 RPM theoretical on a 4S battery. You'd be surprised just how little bite they'll get on average. When I did the math with the previous version, basically what I found was if you're looking at the circle that this sweeps through, these screw heads are about 3.5mm behind this tooth edge on that circle that's swept through. But the drum would have to be spinning at 50% speed on a 12-volt battery to come close to those bolt heads getting hit. Whereas with this, I think there's a pretty similar amount before just this edge of the screw gets hit, and that's really not that big of a deal. So as long as you spin the drum at like 50% throttle or higher all the time, you should be perfectly fine. Another thing I really like is how much more meat there is around the section where the magnet ring exists. This edge right here, I had one of my drums crack, and that is definitely no good. We do not want to invite mega stress concentrations at the weakest part of the drum. So by changing to this style of tooth, we are able to get way more meat in that area and just in general kind of everywhere around the magnet ring. And also keep in mind, I'll hide the magnet ring itself here. Again, I was just trying to show like, this is how deep the pocket goes where it's actually that close to the edge, and then everywhere else it's actually like not close at all to this corner. It just gets close like here. This is the thinnest part, but again, also by far the least likely to get hit as long as the drum is actually spinning at any reasonable speed. And then the stator, that's the biggest, the second biggest change is the way that the stator is designed and how you can do wire management. So what I've told my supplier to do basically is what I want to get shipped to you is essentially this. So there will be a bare PCB that has 3 huge copper pads that you can solder wires directly to if you want. And then in the package, they will include an MR30 PW-M. So this is the PCB mount version of an MR30 connector with a mating connector that has wires as well. So if you want the convenience of just shoving this on, you can. There is one caveat, which is the MR30 is kind of tall. And I was talking a lot with some bot builders who are pretty experienced and some people who tested the SCARABs. They basically all told me, I want this distance as thin as possible because this is kind of a weak point that could get hit. Technically, you can actually pocket this entire PCB plus this. You could pocket this into your uprights, especially if you're 3D printing and you can just make things arbitrarily thicker. Because this isn't spinning. It's not like a belt that needs to be rotating. This is all stationary. So you can actually pocket all this straight into your upright and not have it be exposed. But if you're doing the 102 millimeters between uprights thing and you just have flat uprights like I designed the kit version to have, then you'll have this like 8 millimeters exposed. And I didn't want to extend that to like 10 millimeters, and these connectors are thick. So if you do want to pocket just like, I think it's like 1.3 millimeters. Yeah, 1.3 millimeters into your upright so that you can fit this connector, that's up to you. Or you can just leave off the connector and direct solder. So I'm giving customers the ability to choose that. At least that's the plan right now. And then stator mount, there's 2 M4 screws here. You might think that's not enough, but keep in mind, this shaft is doing everything except preventing the stator from spinning. These 2 M4s, even a single M3 would be plenty for this. These 2 M4s are purely insurance against the entire thing twisting. And if you pocket this into your frame rail, you don't even need to use these because this like huge section here and the huge PCB sticking out here pocketed into your frame rail will obviously also prevent it from twisting. This is just to counter the torque of spin up, the force that happens when the drum spins up. And this drum spins up real fast. It's like a 1 second spin up time, maybe 1.5 seconds. It's on 4S, so it's pretty scary. All right, I think that covers pretty much everything I wanted to cover. I tried to rush order just this aluminum part, so I'm going to be kind of making a weird Frankenstein motor that has the old stator with the new drum at NHRL if it gets here in time. And that, I think, will be a good way to test exactly how much better this design is, if it's better at all, or maybe it catastrophically fails in some way and I'll have to tweak it and fix it. But I think this is a lot more promising personally. So yeah, that covers everything I wanted to say in this video. It's already getting pretty long based on the time codes of recording I've got here. I think we're pushing like 35 minutes of info, but my designer reviews always tend to be pretty long because there's a lot to talk about, especially in this one, as I'm talking about like 2 versions of the robot and an in-depth deep dive on an as of yet unreleased product as well. So if you want to make sure that you're notified when that product actually comes out and you can buy it, or potentially a kit of this entire robot comes out and buy it, make sure to get subscribed and click that bell icon and make sure you turn on notifications. Right now, I think like 5% of people get notified when I produce a video that normally watch my channel. So it would really help me out, and it'll help yourself out as well if you're interested in finding out right away when those things come out and buying them before they go out of stock, which has been known to happen with some of my more popular product lines pretty soon. So yeah, Make sure to subscribe, click the like if you enjoyed this video, and of course, if you like this video, even if you're not going to buy anything, subscribe and hit the bell as well. It really helps me out, and I appreciate everybody you watching. Thank you so much for watching, and have a great week.